For years, artificial intelligence lived entirely in the dark. It couldn't see, it couldn't hear, and it couldn't speak. But today, AI models are absorbing the world through multiple senses at once, taking in sights, sounds, and text, and fusing them together into a single stream of information. To understand this shift, we have to look at the limitations of traditional large language models. These were strict specialists. They worked within a single data modality, which meant they tokenized text strings. You fed text in, and you got text back out. If you wanted one of these text-bound models to examine a photograph or listen to an audio clip, you hit a wall. You couldn't just drop an image file into a text processor. Engineers had to build a bridge between these completely different formats. Because engineers built these isolated, single-task systems, the model's potential was capped. An AI that treats every type of data as a separate, quarantined problem operates more like a fragmented calculator. It lacks a cohesive understanding of how these different inputs relate to one another. The first attempt to fix this sensory isolation was an approach called modular feature-level fusion. This pipeline was created by bolting two entirely separate models together. This diagram illustrates that exact fusion process. A visual asset, like an image, enters a separate vision encoder first. This encoder has to interpret the image before the language model even knows what question you're asking about it. Inside that first node, the encoder extracts specific features from the image and translates them into an array of numbers. It projects the image into a numeric form that the text-based LLM can technically read alongside your prompt. But the transfer between these two models creates a blind spot. Because the encoder processes the image on its own, it inevitably compresses away vital details. The language model never sees the actual image. It only gets a summarized mathematical description of the data. Bolting separate models together creates a translation bottleneck. Instead of observing the real world directly, the AI is stuck playing a game of telephone, relying on a second-hand summary from a secondary system. To bypass that bottleneck, researchers moved away from fragmented pipelines. They designed a single integrated system that processes sight, sound, and text simultaneously, a method known as native multimodality. This star field illustrates the shared vector space, the mathematical foundation where all data types are tokenized together. Instead of translating between different systems, text, images, and audio are all embedded directly into this same high-dimensional space. With text, the model chops words and word fragments into numerical vectors. A word simply becomes a dot in this space, embedded as specific coordinate points. Images are processed the same way. The model takes a picture, slices it into small grid patches, and assigns each patch its own point in that exact same star field. Because everything shares the same mathematical universe, an image of a cat and the text word cat will cluster directly next to each other. They end up in the same neighborhood because their mathematical meaning is identical. Since these distinct data types now live in the same native space, the model attends to text and images at the same time. It no longer requires a translator. It identifies relationships across every format simultaneously. That shared space works well for static data, but video introduces the dimension of time. Early systems attempted to handle video by sampling isolated flat frames, but this approach missed the broader context of movement. If you hand a model a single static image of a person holding a water bottle, it can't determine if they are picking that bottle up or putting it down. A flat frame lacks the sequence needed to understand cause and effect. Native models solve this through spatiotemporal patches. As shown here, the model expands its view along a z-axis, allowing a flat 2D plane to gain depth and become a 3D cube of information. Each 3D token captures a specific area across a short window of time. Because it captures multiple frames at once, the physical movement is mathematically baked into the token itself, rather than being something the model has to guess by comparing separate images. By structuring data this way, the AI can track patterns as they unfold over time. It gains a form of temporal reasoning that allows it to follow sequences and actions within the same architecture it uses for text and images. The shared vector space works in both directions. Just as the model uses it to absorb information, it also uses it to project answers back out. This enables any-to-any generation. The model can take in any combination of senses, like reading a prompt while analyzing a video, and output its response in any combination of formats. If you provide a screenshot of a technical problem on your phone and ask for a solution, the AI doesn't just provide a text explanation. Because it reasons across modalities, it can also generate a custom video tutorial demonstrating the fix. The resulting text, audio, and video are all coherent because they originate from the exact same mathematical source. The model isn't stitching together different outputs, it is expressing a single idea through multiple formats. A moment of wonder. Native multimodality replaces fragmented data pipelines with a system that can process sight, sound, and text as a single, unified signal. By removing the barriers between these formats, AI can finally analyze information with a degree of context that mimics how we perceive the world. The significance of this architecture isn't just the ability to process larger files. It is the model's capacity to understand the intricate, simultaneous relationships between an image, the words that describe it, and the time it takes for an action to occur. These models now integrate sight, sound, and text into a single unified intelligence. Subscribe for more simple AI